Hi everyone, myself Zain Anurali, working as an assistant professor at Maynooth International Engineering College, Maynooth University, Ireland. Today I will present recent ongoing research on control co-design strategy for optimization of heterogeneous autonomous agent formations. In this speech, I will focus on ideas, system level thinking, and conceptual insight rather than heavy mathematical derivations. Some technical details will appear in upcoming publications, but the main goal of today is simple: to explain why control co-design is necessary and how it improves the real-world multi-agent system development. This presentation is organized into 6 acts. We begin with motivation, then move to the control co-design framework, stability analysis, application challenges, and future directions. Now, Act 1. This slide shows the evolution from single autonomous robot to coordinated multi-agent teams. As mission complexity increases, a single agent is no longer sufficient. Tasks such as wide area surveillance, disaster response, or environmental monitoring require cooperation. However, the key challenge emerges when agents are heterogeneous, meaning they have different dynamic sensing and actuation capabilities. Heterogeneity fundamentally complicates coordination and formation control. Growth of multi-agent applications. Here we see how heterogeneous agents, UAVs, UGVs, and marine vehicles collaborate. These formation enables surveillance, infrastructure inspection, disaster response. The key insight is multi-agent formations provide capabilities the single agent simply cannot achieve alone, but coordination becomes significantly more complex. Motivation for control co-design. Modern mission demand cooperation. In practice, deployments naturally involve heterogeneous agents. Different sensing, actuation, energy limits, and dynamics make coordination non-trivial. This motivates a fundamental question: are we designing these systems correctly? Now, the problem statement. The complexity of heterogeneous formations. In heterogeneous formations, agents differ in dynamics. They have sensing constraints, they operate under different energy limits. Intra-agent coupling creates nonlinear and high complex behavior. Swarm, cooperative, and hierarchy formations further complicate coordination. They difficult the difficulty arises not from one agent but from their interactions as well. Traditionally, system design and control design are done sequentially, not together. In heterogeneous formations, this causes dynamics mismatch, constraint violations, and architectural bottlenecks. As shown in figure, the problem appears late at deployment, leading to instability and performance loss as well. Now, in traditional approaches, system design and control design are treated in separate stages. As shown in the figure, the controller is added later and must compensate for fixed system limitations. This separation often leads to reduced performance, poor scalability, and limited adaptability. As a result, there is a clear gap between control theory and real-world deployment. Uh, in the traditional, no, in this slide, why sequential design fail in heterogeneous formations? Traditional sequential design follows system design, then control design, and finally its deployment. In heterogeneous formations, this leads to dynamics mismatch, constraints violations, and architectural limitations. As a result, agents respond differentially, constraints are violated, and scalability is restricted. The key observation is that closed loop behavior is evaluated too late in the design process. This takeaway is clear: design and control must be considered simultaneously. Now, Act 3. This act introduces control co-design as a paradigm shift from traditional sequential design. The key idea is moving from separate stages to integrated thinking. The shift sets the foundation for how co-design improves the system level outcomes. Now, control co-design focuses on simultaneous consideration of design and control decisions. The left figure illustrates how sequential decision constraints later stages. The right figure shows how multidisciplinary integration enables better overall performance of the system. Now, control co-design integrates system design and control design into a single iterative process. Physical system parameters are treated as decision variables, not fixed assumptions. The figure shows an iterative loop between the formation design, control synthesis, and parameter updates. Design decisions are evaluated based on the closed loop formation performance. Now, this act explains why elements are jointly designed in control co-design. Formation layout, actuation, communication limitations, and system architecture are integrated with control design. Co-design replaces late stages fixes with the performance design and system level design as well. Now, control co-design framework for autonomous agent. In this framework, system modeling, control synthesis, and optimization are performed jointly. Design choices are evaluated based on the closed loop behavior, not open loop assumptions. The figure shows as an iterative loop where models, controllers, and design parameters are refined together. This framework systematically balances the performance, cost, and feasibility for heterogeneous autonomous agents formations. Now, agent dynamics and formation layout co-design. Agent dynamics are selected to improve controllability and coordination in formations. Structural parameters are tuned with formation control objectives in our mind. The formation geometry directly affect the stability and convergence behavior. Topology choices influences robustness, communication load, and scalability. As shown in the figure, heterogeneity is explicitly incorporated in both agent design and formation layout. Now, actuation and communication co-design. Control law must respect actuator saturation and physical limits, communication bandwidth and delay constraint feasible coordination strategies. The figure shows joint optimization of actuation and communication rather than treating them separately. Co-design avoids controllers that require unrealistic actuation or communication resources. Now, in Act 5, this act focuses on co-design architectures that balances scalability, robustness, and communication load. We study stability and convergence guarantees under heterogeneous constraints. Performance is evaluated using tracking accuracy, energy efficiency, and robustness in the system. Now, centralized versus distributed co-design architectures. Centralized co-design uses global information to achieve high performance. Distributed co-design relies on local information exchange among agents. The architecture choice directly affects scalability, robustness, and communication load in the system. Selection depend on mission size, communication availability, and reliability requirements. Now, in this slide, stability and convergence via control co-design. Stability and convergence in heterogeneous formations depends jointly on dynamics, topology, and communication. Classic control fails with these elements are designed independently. Control co-design enables Lyapunov-based stability guarantees through integrated design. As shown in figure, a common Lyapunov function links controller structure to convergence to provide the convergence for the system. Now, the performance evaluation and its validation. Now, in this simulation, a heterogeneous multi-agent formation is organized into 6 local groups using a leader-follower structure obtained through control co-design. The agent shows in black are selected as a leader based on optimized control-related criteria, such as lower tracking error, stronger actuation capability, and reduced control effort. These agents are therefore better suited to handle coordination and trajectory tracking tasks. The blue agents act as followers, regulating their motion using relative state information with heterogeneity, and shows how leadership emerges naturally from control co-design process rather being assigned a prior. Now, Act 6, its applications, impact, and outlook. Control co-design enables real-world applications. such as environmental monitoring, disaster response, and infrastructure inspections. The impact includes improved efficiency, enhanced safety, and reduced operational cost. Looking ahead, this work opens direction for emerging technologies, interdisciplinary research, and long-term autonomous system deployment. Now, application domains. Across these application domains, the common challenges are heterogeneity, uncertainty, and limited resources. These challenges are exactly where traditional sequential design fails. Control co-design becomes essential for UAV, UJV, cooperation missions such as surveillance and area coverage. It also enables reliable infrastructure inspection of bridges, pipelines, and power grids. In search and rescue or disaster response, co-design supports robust coordination under failures. For environmental monitoring, it enables long duration, energy aware heterogeneous formations as well. Why co-design matters in practice. Control co-design handles heterogeneity, physical constraints, and communication limits by design, not as afterthoughts. It avoids unrealistic control assumptions that fail in real-world multi-agent system deployments. Co-design enables scalable and robust coordination across large and diverse autonomous teams. Most importantly, control co-design transforms theoretical guarantees into deployable autonomous systems. Scientific and engineering impact. From a scientific perspective, control co-design bridges control theory and system design by treating dynamics, structure, and control jointly. It provides a unified stability and convergence framework for heterogeneous multi-agent formation under realistic constraints. From an engineering perspective, control co-design reduces redesign cycle by avoiding large stage control hardware mismatches. It improves deployment in real-world resources constrained environments. Overall, control co-design changes how we think about designing and deploying multi-agent autonomous systems for our real-world scenarios. Now, limitations and open challenges. Scalability to very large swarms remains challenging due to increased coordination complexity, communication uncertainty, and delays can degrade performance and guarantees. Jointly optimization leads to high computational complexity, especially for large systems. Online adaptation in dynamic environments is still an open research challenge. Now, the future research direction. Deployment of learning-based and adaptive control co-design frameworks for online performance improvement. Integration of digital twin for real-world optimization validation and predictive control. Advancing human swarms interaction and shared autonomy in co-design systems. Extending control co-design to handle the greater uncertainty, scale, and real-world complexity. Now, the key takeaways and conclusion. Control co-design provides a unified system-level approach for designing and controlling multi-agent autonomous formations. It naturally handles heterogeneity by jointly considering dynamics, communication, and architecture of the system. This approach delivers significant improvements in performance, robustness, and scalability over traditional methods. Thank you for your attention. If you have any question, you may just directly ask me via my email. Thank you.